Hello friends, so today we are going to discuss the questions from the year 2024 and there are total of 24 questions, and these questions are from mains as well as advanced. The first question, and it states that when a polarized sheet is rotated between two crossed polarides, then the transmitted light intensity will be maximum for a rotation of. So it means we have two crossed polarides and between them a polarized sheet is being rotated. Okay. So let us assume that I naught is the intensity of the unpolarized light, and then the output from the first will be I naught by 2, and subsequently we are going to write for the, you can say, others also. So in the first part we say that intensity of unpolarized light that is of I naught, and the intensity of the light transmitted from first polaroid, let us suppose that is our I1. So I1 will be equal to I naught divided by 2. You can see intensity of light transmitted from first polaroid if it is given as I1, then this I1 will be equal to I naught divided by 2. And let us assume that the theta is the angle between our first and the second polaroid. Angle between first and second polaroid is our theta, and the angle between the second and third polaroid is our phi. Second and third polaroid is phi, and it is given in the question that both the polarides are crossed with each other. So if both the polarides are crossed with each other, which basically means there are total 3, first, second and third. Okay. So you can say, and the second one is continuously rotated between the two cross polarides. So therefore we can say that first and third polarides are crossed therefore we can write that theta minus phi will be equal to 90 degree, and from here let us find out that our phi will be equal to 90 minus theta. Plus my mistake. And if we say that I2 is the intensity from the second polaroid, intensity from second polaroid, if that is given as I2, then we can write I2 in terms of I1, that I2 will be equal to I1 and cos square of theta, and we can easily substitute our I1, that will be equal to I0 by 2 and giving us cos square by theta. And if I3 is the intensity from the third polaroid, intensity from third polaroid, from third polaroid is of I3. Therefore, we can write I3 in terms of I2. We can say that our I3 will equal to I2 cos square of phi. And we can write I2 in terms of I1 and I1 in terms of I0. So this gives us I1 cos square of theta and multiply by cos square of phi. And finally, we can write our I3 will be equal to I0 by 2 cos square by theta and cos square of phi. And we already know that our phi is equal to 90 minus theta. So we substitute it. We can write this as I0 by 2 cos square theta cos square 90 minus theta, which is our sine square. So we can write this as I square by 2 cos square of theta, and this is sine square of theta. And now we can easily solve it by using the trigonometric identity, and we can write that I3 will be equal to I0 by 2. We can use the double angle, so this will be 2 sine of theta cos of theta divided by 2 and whole square, and this gives us I0 by 8 will be equal to, this will be sine square 2 theta, sine square 2 theta, and we want that our I3 should be maximum, and that is only possible when this sine 2 theta is equal to 1. You can say I3 is maximum when sine 2 theta is equal to 1, or we can say 2 theta is equal to 90. So this gives us that our theta is equal to 45 degree. So option number D is the correct one. Option D is correct. Next question. It states that a parallel beam of monochromatic light of wavelength 500 angstrom is incident normally on the single narrow slit of width 0.001 millimeter. The light is focused by a convex lens on a screen placed in the focal plane. The first minima will be found for the angle of diffraction equal to. So here we have to find out the angle for the first minima, and that is a quite simple relationship. So you can say for first minima, our A sine of theta should be equal to our lambda, and A is our slit width, which is given as single, so this is 0.001 millimeter. So from here we can write that our sine of theta will be equal to lambda by A, or this gives us theta will be equal to sine inverse of lambda by A, and we substitute the values. Sine inverse lambda is our 5000 angstrom, and 0.001 millimeter. So this gives us that our theta will be equal to sine inverse of 1 by 2, giving us theta is equal to 30 degree. So it is, yeah, so this completes this question. We come to the next one. In this question, in a double slit experiment shown in the figure, when a light of wavelength 400 nanometer is used, dark fringe is observed at P if capital D is 0.2 meter. The minimum distance between the slits S1 and S2 is. Okay, so we are given the figure also. In this case, so we have a source and we have two slits, S1 as well as S2. S2 slit is directly in between the source and the point P, and the distance between the source and slit S2 is capital D, and the same distance is between S2 and P also, that is our point of dark fringe observed. And S1 is, you can say, along the hypotenuse of a right angle triangle, so we can easily find out its distance. This distance we can say source to S1, let us denote the source as by S. So we can find out our SS1 will be equal to, this will be d square and plus small d square, and that same will be our S1P also. Okay, so these two will be same. And if you find out the distance between the source and our point P, so we can say our SP will be equal to D plus D, that is equal to 2D. And we are given that dark fringe is observed at point P. So for the dark fringe to observe, the path difference between should be equal to lambda by 2. Okay. So therefore we can write that the path difference for minima at P, path difference for minima at P, that is our SS1 plus S1P minus SP should be equal to lambda by 2. So as SS1P and S1P are equal, so we can simply substitute by twice. This comes as twice d square plus small d square square root and minus SP, that is 2 capital D is equal to lambda by 2. And from here we can just reformulate it. We can write this will be equal to our d square plus small d square square root will be equal to lambda by 4 minus capital D. And if we square it both sides, we are going to get this as d square plus d square will be equal to lambda square upon 16, and this will be plus d square minus this will be lambda t divided by 2, and here d square and d square cancels out, okay. And this gives us that small d square will be equal to lambda square divided by 16 minus lambda d divided by 2, and we already know all these values, so we substitute it and we can get that our d square is equal to lambda is our one second. This looks good. So lambda square was our wavelength is given to us 400 nanometer. So we can write this as 4 into 10 to the power minus 7 whole square, and nanometer is 9, and divided by 2, divided by 16 rather, minus, and this comes as 4 into 10 to the power minus 9. Capital D is given to us as 0.02, so this comes as 0.2 and divided by 2, and sorry, my mistake, yeah, that was correct. This has to be plus because this is minus, so this will be plus and this will be plus and this will be plus. Now it's look good. So we get that our d square will be equal to this 2 goes by 2 and this comes as 10, and this is our 4 into 10 to the power 10, and this also comes as 16 goes by 16, and this comes as 400 nanometer or second, yeah, it's a 400 nanometer. So we get this will be equal to 400 and into 10 to the power minus 10. So this gives us that our D will be approximately equal to 20 into 10 to the power minus 5, or we can also write it as 0.20 millimeters. This is the value of the D. In millimeters is asked, which is 0.20 millimeters. Next question. Given in Young's double slit experiment, light from two identical sources are superimposing on a screen. The path difference between the two lights reaching at a point on the screen is 7 lambda by 4. The ratio of intensity of the fringe at this point with respect to the maximum intensity of the fringe is. So here the path difference is given to us, and that path difference is given to us as by 7 lambda by 4. And this 7 lambda by 4 is also our, you can say, yeah, so we have to find out the ratio of intensity of the fringe at this point where the path difference is 7 lambda by 4 with respect to the maximum intensity of the fringe. Okay, so this is the basic question, and so let's start with the path difference. So we are given that our lambda x, that is our path difference, sorry, not lambda x but delta x. So path difference is our delta x, and that is given as 7 lambda by 4, and we know that the phase difference, if that is represented as phi, phase difference that is over phi will be equal to 2 pi by lambda multiplied by the path difference. So we substitute the value 2 pi by lambda multiplied by 7 lambda by 4, and here lambda and lambdas, and this goes by 2. So we are left with that our phase difference that is over phi will be equal to 7 pi by 2. And we know that the intensity at any point with relative to, you can say, for maximum intensity, and that we can denote by formula. So we can say that intensity at any point if that is given as I, then this I is equal to our I max, and we have the cos square and the phase difference divided by 2, and we already know the phase difference phi, so we are supposed to find out the ratio. So we can write this as I upon I max will be equal to cos square. Phi already we know is our 7 pi by 2, so this becomes a 7 pi by 4, and we can just readjust it. 7 pi by 4 can be written as cos square. This can be written as 2 pi minus pi by 4, which gives us cos square of pi by 4. And cos of pi by 4 is square root of 1 upon square root of 2. Square will be equal to 1 by 2. So we get here I upon I max will be equal to 1 by 2. So the option number A is the correct one. Option A is correct. Next question. It states that in a single slit diffraction pattern, a light of wavelength 600 angstrom is used. 6000 angstrom is used. The distance between the first and the third minima is in the diffraction pattern is found to be 3 mm when the screen is placed 50 cm away from the slits. The width of the slit is, so we have to find out the width of slit in this case, and we are given that the distance between the first and the third minima is given to us a 3 mm. So we can draw a rough approximate figure for that, and so let us suppose this is our slit. It's a single slit, and this is a screen, and screen distance is given as capital D, and single slit width suppose is given as B, and we are given that the distance between the first and third minima, so we can approximately plot the first minima is, let us suppose, at point B, and this is our first minima, let us call this as Y1, and third minima, let us call this as point A. So this is our third minima, so this distance will be our Y3, and we are given that our Y3 minus Y1 will be equal to 3. Okay. That means let us call this as O. So we are given that Y3 minus Y1, let us call that as delta Y, is equal to, this is given as 3 mm, or this can be written as 3 into 10 to the power minus 3 meters. So this is given to us. We can easily find out what will be our y3 and what will be our y1. And here we can make an approximation for the, you can say, small angle. And if required, we can also represent it as y angle. Let us suppose this angle is our theta 1 and this angle will be our theta 2. Sorry, 3. So we have this as theta 1 and this angle as our theta 3. And we know that for nth minima, b sine of theta is equal to n times lambda. And for small angle, you can say for small angle, we can write that sine of theta is approximately equal to tangent of theta. Sine of theta approximately equal to tangent of theta. Therefore, we can write that our b tan of theta is equal to n times lambda, and we can easily write, you can say, this tangent will be equal to our y divided by capital D. So this can be written as b multiplied by the y and divided by capital D. That will be equal to n times lambda, and from here we can write that our y of n will be equal to n lambda capital D divided by b. Okay. And this is the position of the nth minima. Position for nth minima. Now from here we can find out what will be our y1 and what will be our y3. Okay. So we are given that our point B is our first minima. Therefore, we can write our y of 3 will be equal to 3 lambda capital D and divided by B. And we have A is our third minima. Sorry, it has to be 1. And A is our third minima. Therefore, we can write that our y3 will be equal to 3 lambda D divided by B. And the difference between the two is given to us. So we can use that our y3 minus y1, which is our 3 lambda D B minus lambda D upon B, is equal to 3 into 10 to the power minus of 3. And this lambda and capital D values are given to us. Therefore, we can write that our B will be equal to, this comes as 2 lambda by B. Okay, so we can write this as 2 into 6000 10 to the power minus 10 multiplied by 0.5 and divided by 3 into 10 to the power minus 3. And this gives us that our B is equal to 2 into 10 to the power minus 4 meters. And in the question we are given that our B is equal to, sorry, we have B is equal to 2 10 to the power minus 4. So this will be equal to 2 into 10 to the power minus 4. So therefore let us call this as x. So we can say that our x is equal to 2. Next question. And here it was asked that the diffraction pattern of a light of wavelength 400 nanometer diffracting from a slit of width 0.2 millimeter is focused on a focal plane of convex lens of focal length 100 centimeter. The width of the first secondary maxima will be. So here we are supposed to find out the width of first secondary maxima. So this is based on, you can say, formula itself. We already know that the width of first secondary maxima is lambda divided by A and multiplied by capital D, where A is the slit width and D is the distance given. So we know that width of first secondary maxima is equal to lambda A upon multiply by capital D, and here it is given that is focused on a focal plane of a convex of focal length 100 centimeter. Okay, so it means the screen will be at a distance of capital D, which is about 100 centimeter. So this is about capital D. So we substitute the values, we get lambda is given to us as 400 nanometer. So this becomes 400 into 10 to the power minus 9, and capital D is about 100 centimeter, 100 into 10 to the power minus 2, and A slit width is given as 0.2 millimeter, and this comes as minus of 3, and this is about close to 2 millimeters. So option number A is the correct one. Option A is correct. Next question. It states that a beam of unpolarized light of intensity I0 is passed through a polaroid A and then through another polaroid B, which is oriented so that its principal plane makes an angle of 45 relative to that of A. The intensity of the emergent light is. So here we are given a unpolarized is our I0, which is passed through a polaroid A and then through polaroid B. The angle between A and B is said to be given as 45 degree. So we can write that intensity from the polaroid A from polaroid A, let us suppose that is given as IA, that will be equal to I0 unpolarized divided by 2, and the angle between A and B is 45. Therefore we can write that intensity from polaroid B let us suppose that is given as IB, which will be equal to IA, and we have cos square of 45, the angle between the two. IA is already, we know, is I0 by 2, so we substitute it, we get our IB is our I0 by 2, and this comes as 1 upon square root of 2 whole square, and this gives us I0 by 4. Therefore our IB is equal to I0 by 4. So option number A is the correct one. option A is correct. Next question. It states that two waves of intensity ratio 1:9 cross each other at a point. The resultant intensities at the point when A, okay, so there are two conditions: when waves are incoherent is I1, and B, when waves are coherent is I2, and differ in phase by 60 degree. If I1 by I2 is 10 upon x, then the value of x is. So here we are given that they are having intensities, that is our I1 and I2, and they are respectively for incoherent as well as coherent. So we can write, or we can say we know the formula for coherent and incoherent. Okay. So we can write that for incoherent wave, intensity is given as I1. So we can write that I1 will be equal to, there are two waves. Let us suppose one wave is represented as IA, intensity is IA, and another wave is represented as intensity as IB. So this will be equal to IA plus IB, and the ratio is given as 1:9. So in terms of ratio, we can write that our I1 will be equal to IA, we can write in terms of 1 I0, and IB is our 9 times I0, and this comes as 10 I0. Similarly, we are given that for coherent wave, that is our I2 will be equal to IA plus IB, and this is plus 2 square root of IA, and sorry, let me, this is given as our I2. So we can write that our I2 will be equal to IA plus IB plus twice square root of IA IB, and the angle between them is about 60, so this becomes cos of 60. So once again, IA is our I0 plus 9 I0, and this comes twice. We have here 1 I0 multiplied by 9 I0 and cos of 60. So we get that our I2 will be equal to, this will be our 13 I0, and we need to find out ratio of I1 to I2. So therefore I1 to I2, I1 is our 10 I0, and I2 is our 13 I0, and here I0 and I0 goes away, so this comes as 10 upon 13, which means that x, we are given that the solution is 10 upon x, so which will be equal to 10 upon 13. So this gives us that our x will be equal to 13. Next question. It says that when unpolarized light is incident at an angle of 60 degree on a transparent medium from air, then a reflected ray is completely polarized. The angle of refraction in the medium is. So here we have to find out the angle of refraction. Condition is that the reflected ray is completely polarized. So we can just draw a approximate figure for that. And suppose this is the plane, and we have a ray that is incident, and with respect to the normal, it is making an angle of 60 degree, and we have a refracted ray and we have a reflected ray, and it is between air and some medium. So this is our air and this is some of our medium. So by Brewster's law we can easily see that for the completely refracted ray, the angle between the reflected and refracted ray is equal to 90 degree. So you can say from Brewster's law, angle of refraction Brewster's law, we can say angle between refracted ray and a reflected ray is 90 degree. And we need to find out the angle of refraction. So angle of refraction will be coming as, and we already know that the angle of incidence is our 60 degree. Okay. So therefore we can say that the angle of refraction will be equal to 30 degree. Next question. Okay, 30. Option number A is the correct one. Option A is correct. Next question, and it states that a monochromatic light of wavelength 6000 angstrom is incident on a single slit of width 0.01 millimeter if the diffraction pattern is found at the focus of convex lens of focal length 20 centimeter. The linear width of the central maxima is. So here we are supposed to find out the linear width of the central maxima, and it is a, you can say, single slit so it is, we can just use the direct formula, and it states that the linear width represented as W will be equal to 2 lambda small d divided by A. A is the width, lambda is the wavelength, and you can say the focus is because of the focal length of 20 centimeter. So the screen will be at a distance of 20 centimeter. Okay, so we substitute the values. We can write that our W will be equal to 2 into lambda is our 6000 into 10 to the power -9, and D is given to us as 20 centimeter. This comes as 0.2, and A is given to us at 0.01 millimeter. So this becomes 1 into 10 to the power -5. So we get our W is equal to 24 millimeters. So option number B is the correct one. option B is correct. Next question. It states that a microwave of wavelength 2 cm falls normally on a slit of width 4 cm. The angular spread of the central maxima of the diffraction pattern obtained on the screen is on a screen 1.4 meter away from the slit will be. So here we are supposed to find out the angular spread. Okay. And we know that for the first minima, the A sine of theta will be equal to lambda. So you can say that for first minima, A sine of theta will be equal to lambda, or we can say that our sine of theta is equal to lambda by A, which gives us that our theta is equal to sine inverse lambda by A, and lambda is given to us as 2 cm and width is given to us as 4 cm. So this becomes sine inverse of 2 by 4, which gives us 1 by 2. So therefore our theta is equal to 30 degree, but we need to find out the angular spread. Angular spread will be equal to twice of this angle. So we get our angular spread will be equal to 2 theta, because it is uniform on the top side as well as the bottom side. So this comes as 2 into 30, that is over 60 degree. So option number C is the correct option. C is correct. Next question, and it states that in Young's double slit experiment, monochromatic light of wavelength 5000 angstrom is used. The slits are 1 mm apart and the screen is placed 1 meter away from the slits. The distance from the center of the screen, where the intensity becomes half of the maximum intensity for the first time, is. So we have to find out the intensity where it becomes half of the maximum intensity for the first time. So let us assume that the intensity because of each slit on the screen is I naught. So intensity at the center of screen will be equal to 4 times I naught, because there it is a central maxima. So you can say that intensity of light on screen due to each slit is our I naught, and from here we can say the intensity at the center of screen center of screen will be equal to 4 times I naught, because each slit, there are 2 slits and each is having a I naught intensity. And also we know that the formula for the intensity at a distance y from the center, intensity at a distance y from the center, if given as I, then this I will be equal to I naught plus I naught 2 times I naught square root, and this comes as cos of phi. And our maximum, that is our I max, is equal to 4 times I naught. Our I max is equal to 4 times I naught, and from here we can write that our I max by 2 will be equal to twice I naught, and we can substitute value of here I naught. So this gives us that our this will be equal to twice I naught plus twice I naught and cos of phi. Sorry, not I naught, but I only. One second, let me check whether it is I or I naught. The distance from center, half of the maximum density. Okay, so this is I, and I we already know this equation. So it comes as 2 I naught and 2 I naught plus 2 I naught cos of phi. Therefore, we can write that our cos of phi will be coming equal to as 0. So this gives us that cos of phi is equal to 0, and which gives us that phi is equal to pi by 2, and the phase difference is pi by 2. So this is our phase difference, and we already know that our phase difference can be also written as 2 pi by lambda multiplied by d sine of theta is equal to the phase difference, that is our pi by 2. And from here, sine of theta can be approximately equal to tangent of theta, small angle. So you can say sine of theta is approximately equal to tangent of theta, and this gives us y upon capital D. Therefore, we can write this as 2 pi d by lambda multiplied by y by capital D is equal to pi by 2, and pi cancels out. So we can write this as y is equal to, we come as lambda d, and this is our 2 multiplied by small d. Now we can easily substitute the values. We get this as 5 into 10 to the power minus 7 into 1, 4 into 10 to the power minus 3, and this comes as 125 into 10 to the power minus 6, but we are already given that, let us put this is x multiplied by 10 to the power minus 6 will be equal to 125 10 to the power minus 6. This gives us that our x is equal to 125. Next question, and it states that the distance between the object and its 3 times magnified virtual image as produced by a convex lens is 20 centimeter. The focal length of the lens used is dash centimeters. So we have to find out the focal length of the lens used. Okay. And we are given that the distance between the object and its 3 times the magnified virtual image. Okay, so we are given a magnification that is 3, and distance between the object and virtual image is given as 20 centimeter. So these two are you can say the formula that is which we normally use is the relationship between the focal length, the object distance and the image distance is given in this question in a different way. We are not given the distances with respect to the pole, but we are given the distances with respect to each other between the image as well as in terms of the object. So you can say distance between object and its virtual image, distance between object and its virtual image it is given as 20 centimeter. Therefore, we can write that V minus U will be equal to 20 centimeter. V minus U will be equal to 20 centimeter, and we are also given that the image is virtual and magnified 3 times. So we are given that image is virtual and magnified 3 times. Therefore, we can write that our V is equal to 3 times U. So from here we can use that, let us call this as 1. So we can say from equation 1 we can write this as 3U minus U is equal to 20. This gives us that U is equal to 10 centimeter. Mean distance of the object from the pole is 10 centimeter, and we can write that our V is equal to thrice 10, which gives us that V is equal to 30 centimeters. And it is given that the image is virtual, therefore both U and V will be negative. We are given that image is virtual, so which means that U will be equal to minus of 10 and V will be equal to minus of 30. Now we can use the lens formula and substitute the values. Lens formula is our 1 upon F is equal to 1 upon V minus 1 upon U, and we substitute, we get 1 upon F is equal to minus 1 upon 30 minus and minus of 10. So we get 1 upon F is equal to 1 upon 15. This gives us the focal length is about 15 centimeters. So yeah, for 15 centimeter. Next question. It says that the refracting angle of a prism is A. The refractive index of the material of the prism is cot A of A by 2. The angle of minimum deviation is. So here we have to find out the angle of minimum deviation, and we are given the refractive index, that is mu is given as cot A by 2. And the standard formula for the refractive index for the minimum deviation can say refractive index for minimum deviation. We can write that our mu is equal to sine of A plus delta of m divided by 2, and this is sine of A by 2, and mu is given as cot A by 2. So we substitute it, we get cot A by 2 will be equal to sine A plus delta m by 2, and here we have sine A by 2. Now it's a simple trigonometric formulation. Cot, we can write it as cos A upon sine A by 2, and sine A by 2, sine A by 2 cancels out. So we can write this as cos A by 2 sine A by 2 will be equal to sine of A plus delta m by 2, and this comes as sine of A by 2. Sine A by 2, sine A by 2 goes away, and we are left with cos A by 2 is equal to sine A plus delta m by 2. So we can write this as cos A by 2 is equal to sine A plus delta m divided by 2. And this cos A by 2, we can write it as sine of 90 minus A by 2. So we can write this as sine of 90 minus A by 2 is equal to sine of plus A by 2. So this gives us that 90 minus A by 2 is equal to A plus delta m divided by 2. Here delta m is the minimum deviation angle, and this gives us 180 minus of A is equal to A plus delta m. Therefore delta m will be equal to 180 minus 2A. So this is the angle of minimum deviation, 180 minus 2A. That option number A is the correct one. Option A is correct. Next question. It states that a convex lens of focal length 40 cm forms an image of an extended source of light on a photoelectric cell. A current I is produced. The lens is replaced by another convex lens having the same diameter but focal length is 20 cm. The photoelectric current is now. So here you can say we are interested in finding the photoelectric excuse me please, photoelectric current, and the photoelectric current is directly proportional to the number of photons striking the surface per second. It doesn't depend upon how the light is concentrated or the concentration of light. Okay, so it means it is independent of the lens, because the convex lens is of different focal length is being used, that is 40 cm and 20 cm. This is only going to change the amount of the light that is being concentrated. So it's not going to change the, you can say, the number of photons striking the surface. You can say that in photoelectric effect, current I is directly proportional to number of photons striking the surface per second. Number of photons striking surface per second. And we can also write that not how concentrated light is. Not how concentrated light is. So therefore, the intensity of the light is going to remain same. That the option A4 is the correct one. 4 is correct. Next question. It states that two immiscible liquids of refractive index 8/5 and 3/2 respectively are put in a beaker as shown in the figure. The height of each column is 6 cm. A coin is placed at the bottom of the beaker. For the near normal vision, the apparent depth of the coin is alpha by 4 cm. Then the value of alpha is. So here we have two liquids, both having different refractive index, and we have to find out the apparent depth because of these two liquids. And the apparent depth of two liquids is the apparent depth because of the summation of the apparent depth because of the individual liquids. So we can just write the formula directly. We can say that height apparent will be equal to h1 and its refractive index mu1 plus h2 and its refractive index mu2. Height is given to same in both the cases, so we can write this as 1 upon 3/2 plus 1 upon 8/5. So this gives us that our h apparent will be equal to 1/4 centimeters, and which is given as alpha by 4, and therefore the alpha is equal to 31. Okay, this was quite straightforward. Next question, and it states that we have a convex mirror of radius of curvature 30 cm forms an image that is half the size of object. The object distance is. So here we are given that the image is half the size of the object, and we have to find out the object distance. So in this case we are going to use two formulas. One is the formula for the convex mirror and another one is for the magnification. Okay. So magnification, okay. First of all, we are given a radius of curvature. From here we can find out the focal length. So we can say the focal length of the convex mirror convex mirror, if given as f, will be equal to r by 2, and that comes as 15 centimeters. And we also know that the magnification m is our height of the image and height of the object, which is also our minus v upon u, and magnification is said to be given as half. So therefore we can write that our half will be equal to minus v upon u, and from here we can find out that our v is equal to minus u by 2. Now we can use the mirror formula. And mirror formula gives us 1 upon f is equal to 1 upon v plus 1 upon u, and 1 upon f we already know is 15, so we substitute it, we get 1 upon 15. V we just found out in terms of u, that is minus u by 2, and this is plus 1 upon u. So we can easily solve it for u. This gives us minus 1 upon u is equal to 1 upon 15. So we get u is equal to minus 15 centimeters. So we have option number 1 is the correct one. Option 1 is correct. Next question, and it states that a biconvex lens of refractive index 1.5 has a focal length of 20 cm in air. Its focal length when immersed in a liquid of refractive index 1.6 will be. And in this case, we are given that we have a refractive index whose a lens is given whose refractive index 1.5. Air we know is refractive index 1. Air is you can say 1, and the liquid is given as 1.6, and focal length is given as. So here we are going to use the lens maker formula. So we can say that our lens maker's formula, which gives us 1 upon f is equal to n minus 1, and 1 upon r1 minus 1 upon r2. And here n is our, you can say, relative refractive index, and if the lens is in the air, then n will be equal to the refractive index of the liquid divided by air, and when it is a medium, it will be liquid divided by the medium. So let me, n is relative refractive index with respect to surrounding medium. Surrounding medium. So therefore, we can write that for lens in air, our n will be equal to refractive index of the lens and refractive index of the air. Air we know is 1, so this comes as refractive index of the lens. And when the lens is in the liquid, so you can say for lens in a medium, then our n will be equal to refractive index of the lens divided by refractive index of the medium. This is the only difference. Rest of the things will be quite simple to solve it. So first medium is given as air, and the second one is our liquid. So we are going to solve it for the air first. You can say for air, 1 upon Fa will be equal to refractive index of the lens, and this comes as 1 upon R1 minus 1 upon R2. In fact, focal length is 1 upon 20, sorry, it is 20, so get 1 upon 20, 1.5 minus 1, and 1 upon R1 minus 1 upon R2. So here, from here, we are going to find out our 1 upon R1, 1 upon R1 minus 1 upon R2, minus 1 upon R2. This comes equal to as 1 by 10. And now the medium is the liquid. So we can say for liquid, our focal length for the medium is equal to refractive index of lens, refractive index of medium minus 1, and 1 upon R1 minus 1 upon R2. So we get 1 upon Fm is equal to 1.5 divided by 1.6 minus 1, and we just found out our 1 upon R1, 1 minus 1 upon R2 is 1 upon 10. So this gives us that our focal length Fm will be equal to minus 160 centimeters. So the option number 2 is the correct one. Option 2 is correct. Next question, and it states that the distance between object and its two times the magnified virtual image produced by a curved mirror is 15 centimeter. The focal length of the mirror must be. Okay, so distance between the object and its virtual image, which is magnified 2 times, is given as 15 centimeter. So here also the distance is not given with respect to the pole, but is given with respect to each other, and the magnification is also given as 2 times, and the image is said to be virtual image. So we start with the magnification, and we know that magnification is given as 2, which is our minus v upon u, and our second thing is given that the distance between the object and the image is 15 centimeter. So we can write that our v plus u will be equal to 15 centimeter. V plus u is equal to 15 centimeters. And we can also, if required, draw the approximate figure. So this is a mirror. Suppose we have an object somewhere here, and the image is somewhere here because we govern virtual. So this distance is our u, and this distance is our v, and this total distance is given to us as 15. Okay, so you can just draw it, and from here we can write that our v is equal to 15 minus u. We substitute it in the equation for the magnification, and we get this as 2 will be equal to minus, and this is our 15 minus u, and divided by minus of u. This gives us our twice of u is equal to 15 minus u, and this is our 3u is equal to 15, giving us u is equal to 5 centimeters. Therefore our v is equal to 15 minus 5 is equal to 10 centimeters, and we need to find out the focal length, so we can use the mirror formula. Mirror formula gives us 1 upon f is equal to 1 upon v plus 1 upon u. V is our 1 upon 10 plus u is our 5. One second. Yeah, u is 5, so this becomes minus of 5, and we get our 1 upon f is equal to 10 is LCM, so this becomes 1 minus 2, giving us minus upon 10. So focal length is equal to minus 10 of centimeters. Therefore, option number C, 3 is the correct one. Option 3 is correct. Come to the next question. Here it is given that the distance between the object and its 2 times magnified real image is produced by a convex lens is 45 centimeter. The focal length of the lens used is. So it is just same question as we did previously, only difference is that there is a convex lens and the real image. This is the only difference. And we start with the magnification once again. So we have a magnification that is equal to our minus of 2 is equal to V upon U, and this gives us that V is equal to minus of 2 multiplied by U, and the image is real. So we have our real image, and therefore our V minus U will be equal to 45. So we can easily substitute it. V is our minus of 2U, so this comes as minus of 2U minus of U is equal to 45, giving us U is equal to minus of 15 centimeters, and therefore our V is equal to, this comes as 30 centimeters. Now we can use the formula, lens formula, that is our 1 upon F is equal to 1 upon V minus 1 upon U. So this gives us 1 upon 30, minus minus plus will be 1 upon 15. So our LCM is our 30, so this becomes 1 plus 2, that is equal to 3 by 30, giving us that the focal length F will be equal to plus 10 centimeter. Next question. So in this question, it is said that in an experiment to measure the focal length F of a convex lens, the magnitude of object distance x and the image distance y are measured with reference to the focal point of the lens. The y-xy plot is shown in the figure. The focal length of lens is. So we are given this particular graph, and herein the important part is that the distance is measured with respect to the focal point, not with respect to the pole. Okay, so actual distance of the, you can say, the image and the object is going to now with respect to focal, because the distance is given with respect to the focus. So we know the lens formula, which gives us one upon F is equal to 1 upon V minus 1 upon U, and the distance is measured with respect to focal point. Distance of object and image is measured with respect to focal point. Therefore, we can write that our U will be equal to x plus f and our V will be equal to y plus f. So if we substitute it, we get 1 upon f is equal to 1 upon y plus f minus 1 upon x plus f. and this is u and v. Okay, so u will be our minus, so this will be going as minus, and the respective distances for point C is our x and y are 20. Therefore, we can write this as 1 upon f plus 20 plus 1 upon f plus 20. So we get this as 1 upon f is equal to 2 upon f plus 20. This gives us that f plus 20 is equal to 2f, or we can say f is equal to 20 centimeters. Next question. It is said that light from a point source in air falls on a spherical glass surface mu 1.5 and a radius of curvature r 20 centimeter. The distance of the light source from the glass surface is 100 centimeter. The position of the image is formed at. So here we are given a spherical surface. So we are going to use the refraction formula for a spherical surface, and all the values are given to us. We can directly substitute the values. So we know that for spherical surface, mu2 by v minus mu1 upon u is equal to mu2 minus mu1 upon r. And we have to remember that mu1 is the incident medium and mu2 is the refractive medium. And here incident medium is our air, and we are given that the u is given to us 100 centimeter. So u will be equal to minus of 100, and our mu2 is equal to 1.5, and we have our mu1, that is of air, is equal to 1, and we have radius of curvature is given as 20, so r is equal to 20. So if we substitute the values, we get this as mu2 is our 1.5, so 1.5 divided by v plus mu1 is our 1 upon u is our 100. This comes as 1.5 minus 1 divided by r is given as 20. So this gives us that our 3 by 2v is equal to 1 upon 40 minus 1 upon 100. Therefore, our v will be equal to, and this comes as 2 by 3, and here we can write that our LCM will be equal to 200, and this comes as 5 minus 2, that is 3, so this goes away and this goes by 100, so we get our v is equal to 100 centimeters. Next question. So this was asked in the 2024 advanced question. As previous were all of mains, and it states that two equilateral triangular prism P1 and P2 are kept with their sides parallel to each other in vacuum, as shown in the figure. A light ray enters prism P1 at an angle of incidence theta such that the outgoing ray undergoes minimum deviation in prism P2. If the respective refractive indexes of P1 and P2 are square root of 3 by 2 and square root of 3, then theta is given to us by sine inverse square root of 3 by 2 sine of pi by beta, where the value of beta is. So we have to find out the value of beta. And here we have to remember one thing, that for the minimum deviation which is taking place in the prism P2, the refracted ray will be parallel to its base. Okay, and these are the equilateral prisms, so all angle will be equal to 60 degree. So here we can just draw an approximate figure, and this is, let us suppose, bends like this, and we have a normal here, and it bends goes like this, and here also normal, and in this P2 it has to be parallel with the base, and then normal, and it will be bending like this. Okay. So let us call this as P, this is a Q, this is a R, and we have a S, and this is T, and that is our U. So let's use the, okay, and here ST, let me call this as A, B, C, and this is X, Y, and Z. So for minimum deviation in P2, for minimum deviation in P2, ST should be parallel to XY, and all angles are of 60 degree. So this here was 60, all of the angles are 60. Okay. Therefore, we can easily say that this angle is also over 60 degree, and therefore we can write that angle, if it is parallel, then we can say angle TSZ. TSZ will equal 60 degree, which gives us that the angle, this angle will be over 30 degree. So we can call this as, let us call this as R1, this as R2, R1, R2, and let us call this as R3, and this as our R4. So if angle TSZ is 60 degree, therefore we can say our R3 will be equal to 30 degree. And if we use this is theta, and let us call this as angle as I. So Snell's law at point S. Snell's law at S, and that we can easily say at S, we can say that our it is in vacuum, so we can say 1 multiplied by sine of I is equal to, and that is our refractive index of P2 and sine of R3. So we can say our sine of I is equal to square root of 3, and here we have sine of 30 degree. Therefore we get that sine of I will be equal to root 3 by 2. Sine of I is equal to root 3 by 2. giving us that the angle of I is equal to our 60 degree. So we found out the angle of incidence is equal to 60 degree, and we have two normals. Let us call this as three normal, rather n1. This is normal n2, this is normal n3. Normal n2 and n3 are parallel with each other. You can say normal this is our n2 and this is our n3. Let me draw it here. So we have these two are the parallel surfaces. This is our A and this is our C, and we have this as X and Z. So this is our X and Z. One normal is here and another normal is this one. So this is our n2 and this is our n3, and we found out that this particular angle is our 60 degree. Okay. So we can say that our n2 is parallel to n3. Therefore, let us call this as angle as I1. So we can say our I1 will be also equal to 60 degree. Therefore, we can use, and this is our point R. And here we have a refractive angle of R2. So ray of light is coming something like this, and this angle is our R2. So Snell's law at R this gives us that our refractive index is given to us as square root of 3 divided by 2 sine of R2 is equal to 1 multiplied by sine of I1. Sine of I1 is sine of 60, and we can write this as sine of 60 will be equal to our square root of 3 divided by 2, and therefore we can write that our sine of R2 will be equal to square root of 3 divided by 2 multiplied by square root of 2 and square root of 3. Square root 2 and cancels out, and this comes as 1 upon square root of 2, which gives us that our R2 is equal to 45 degree. R2 is equal to 45. Okay, so we found out our R2, and this is the second prism, and we have this as R1, and this angle is 60 degree. And we know that the angle of prism is equal to R1 plus R2, that is our A, and this is our P1 prism. This is P1 and this is our P2. So we can write for P1 A will be equal to R1 plus R2, which gives that 60 is equal to R1 plus 45, giving us that R1 is equal to 15 degree, and which can be written as pi by 12. Now we are into prism P1, and the face is our AB. So let me draw it here. So this is our A, B. The beam of light is reflecting here. This angle is theta, which we are supposed to find out, and this angle we just found out is our 15 degree, which was our R1. This point is P. So we're using Snell's law at P. Snell's law at P, we get this as 1 sine of theta is equal to square root of 3 divided by square root of 2, and we have sine of pi by 12. Now it's a simple calculation. Here we get that our theta is equal to sine inverse of square root of 3 divided by 2, and we have sine of pi by 12. But we are given that this theta is equal to square root of 3 sine pi by beta. So we are given that of theta is equal to sine inverse of square root of 3 by 2 and sine of pi by beta. So 1:1 comparison gives us that the beta is equal to 12. Next question. It was also asked in the 2024 advance, and it states that in a Young's double slit experiment, each of the two slits A and B, as shown in the figure, are oscillating about their fixed center with a mean separation of 0.8 mm. The distance between the slits at time t is given by d is equal to 0.8 plus 0.08 sine of omega t millimeter, where omega is 0.08 radian per second. The distance of the screen from the slit is 1 meter, and the wavelength of the light used to illuminate the slit is 6000 angstrom. The interference pattern on the screen changes with time, while the central bright fringe, that is zeroth fringe, remains fixed at O. So based on this entire description, we have two questions. In the first part, it says that the 8th bright fringe above the point O oscillate with the time between two extreme positions. The separation between the two extreme positions in micrometer is. And the part B, the maximum speed in micrometer per second at which the 8th bright fringe will move. So this is a figure. This figure is quite simple. We have two slits A and B, and the respective distance between A and B is given as d. And we have a parallel beam of light that is falling at A and B. And we are given that the central bright fringe do not move. It is fixed. First of all, we are given the mean separation between the slits is governed by the equation. And that equation is, you can say, a time dependent equation. Okay. So we are given that mean separation between the slits that's our d is equal to 0.8 plus 0.04 sine of omega t, and omega is given to us, that is about 0.08 radian per second, and the distance between the screen is given as 1 meter. Wavelength is also given. Okay. So first of all, we are going to find out the position of the bright fringe, okay, which is fixed. Okay. So we can say that position of the bright fringe, and the general formula for the nth bright fringe, that is our y of n, is equal to n lambda, and we have this as capital D divided by small d, and this is the position of the nth bright fringe. Position of nth bright fringe. Therefore, from here we can write the 8th bright fringe, that is y of 8 will be equal to 8 lambda capital D divided by D, and which is a time dependent. If we substitute all the values, we get this is 8 multiplied by 6 into 10 to the power minus 7. Distance is given as 1 and d of t is given as 0.8 plus 0.04, and we have sine of omega t, and this is millimeter, so comes as 10 to the power minus 3. And we can just sort it out, and we can write this as that our y of 8 will be equal to 4.8 into 10 to the power minus 3, and this comes as 0.8 plus 0.04, and we have this as sine of omega t. Now we are going to find out the maximum and the minimum values of y of 8 that is dependent upon t with respect to time t. Okay, and this entire function is dependent upon sine of omega t. You can say maximum and minimum values of 8th fringe with respect to time t, and we know that the sine of omega t, it varies from -1 to +1. Therefore the minimum, you can say, slit separation, therefore we can write that our d max will be equal to 0.08 plus 0.04 multiplied by 1, giving us 0.84 millimeter, and similarly we have d minimum will be equal to 0.08 plus 0.04 and minus 1, this gives us 0.76 millimeter. Now we can find out the minimum position and the maximum position, and remember, we have to remember that this sine of omega t is in the denominator. Okay, so it will be the reverse. So we can say the minimum position this is going to happen when the split is our d max. Okay, then only we are going to get the minimum position. Therefore we can write that y minimum is equal to 4.8 into 10 to the power minus 3, and this maximum is 0.84, and this comes as 5714 micrometer. Maximum position this maximum position is when our t is our minimum. So we get our y max will be equal to 4.8 into 10 to the power minus 3, and if it is a 0.76, which comes as 6316 micrometer. So total oscillation range, that is delta of y, will be y max minus y mean. So you can say total oscillation range, that is our delta of y, will be equal to y max minus y mean. We substitute the values, we get delta of y is equal to 6316 minus 5714, which gives us 602 micrometers. Yeah, so first is done. Now we come to the second, where we are required to find out the speed. Part 2. We already know the expression for our y of t. We know that our y of t is equal to n lambda capital D divided by small d, and we 8 10 to the power minus 6, and this comes as 0.8 plus 0.04 sine of omega t. And for the sake of convenience, let us assume that this factor is represented as a. So we can write that our y of t is equal to a divided by 0.8 plus 0.04 sine of omega t. And we are interested in the velocity, so we can just derivate it. So we can write, taking derivative, we get our v of t is equal to dy upon dt. So this gives us that v of t is equal to d of dt, and we have this is a divided by 0.8 plus 0.04 sine of omega t. And by using the chain rule, we can just derivate it, and we get the equation that v of t will be equal to minus of a. This comes as 0.04 omega cos of omega t, 0.8 plus 0.04, and we have a sine of omega t, and this will be our whole square. And for, we can say, magnitude of maximum speed, magnitude of maximum speed, that is our cos of omega t is equal to 1, and the denominator is minimum because we need speed to maximum, so cos of omega t should be equal to 1, and the denominator function that is our sine of omega t should be equal to 0. So from here we can say our d should be equal to 0.8 millimeter. Therefore our V max will be equal to 4.8 into 0.04 and multiply by 0.8, and this is 0.8 and its whole square, 10 to the power minus 6. So we get that our V max will be coming equal to as 2.4 into 10 to the power minus 8, and this is our 0.024 micrometer per second. Okay, I forgot to convert this one. This is millimeter. Okay. So let me correct it here. This comes as into 10 to the power minus 3 and this is whole square. So this comes as 24 into 10 to the power minus 6 and will be equal to 24 micrometer per second. This is 24, not 2.4. 24. So I think this was, yeah, in micrometer per second. So these were the question that was asked in the year 2024, mains and advanced. This completes all the questions. Thank you.